Have you at any point analyzed whether we're truly alone in the universe, or is there something else to our reality beyond what we see and envision? Assuming the James Webb Telescope finally uncovers that we live inside a black hole, join us as we explore this groundbreaking news that will make you question everything you thought you knew about the universe. So, what exactly are black holes? They're like something out of a terrifying nightmare. Sure, you might have seen them in science fiction movies, but they are far more alarming in reality. Black holes are not fictitious. They are real, as confirmed by experts. Essentially, black holes are massive amounts of matter compressed into an incredibly small region. Picture a star, typically more massive than the Sun, all compacted into a sphere the size of New York City. The gravitational pull is so extreme that nothing, not even light, can escape from it. Scientists have been fascinated by black holes for decades. These objects in space are so massive and dense that they can trap light. The most notable theories about black holes were predicted by Einstein's theory of general relativity. Essentially, when a massive star reaches the end of its life, it collapses, leaving behind a dense core. If the mass of this core is several times that of the Sun, gravity overwhelms everything, leading to the formation of a black hole. It's challenging to detect black holes as they emit no light. However, scientists have found ways to infer their presence by observing their effects on nearby matter. For instance, if a black hole passes through a mass of interstellar matter, it will pull that matter toward it in a process called accretion. Furthermore, when an ordinary star gets too close to a black hole, it can be torn apart, emitting X-rays as it is consumed. Black holes also have immense effects on their surroundings. They can devour nearby stars, emit powerful gas jets, and even influence the formation of new stars in certain regions while slowing it down in others. But where do black holes come from? Imagine stars, once massive and vibrant, meeting their tragic end in a dramatic event known as a supernova. From the remnants of these fallen giants, black holes are born. Most black holes originate from massive stars that end their lives in supernova explosions. Smaller stars, when they die, transform into neutron stars, which are incredibly dense but not dense enough to trap light. If a star is several times the mass of our Sun, it collapses under its own gravitational force, forming a black hole. As these collapses occur, something strange happens near the surface of the black hole. Time itself begins to behave oddly. From the perspective of someone far away, time appears to slow down near the event horizon, the point beyond which nothing can escape. It's as if the star's clock ticks at a different speed compared to our own. Sometimes, when two smaller black holes collide, they merge to form a much larger and more terrifying black hole. If a black hole interacts with a neutron star, it creates an enormous phenomenon that defies observation. Scientists have tried to understand the scale of these massive phenomena for years. Black holes come in two sizes, small and large. But small is relative when it comes to black holes. Stellar black holes, the remnants of large stars, can be as large as 10 times the size of the Sun. There may be up to 10 million to a billion of them in the Milky Way alone, a staggering number of black holes that could devour anything in their path. However, there's something even more immense at the other end of the spectrum. Supermassive black holes. These can be millions or even billions of times larger than the Sun and exist at the center of massive galaxies, including our own Milky Way. They are like enormous dark voids, pulling everything toward them. Famed physicist Stephen Hawking dedicated much of his life to studying black holes. His lectures were always captivating, but some of his theories couldn't be confirmed due to a lack of advanced equipment. But hope lies on the horizon, and it comes in the form of a single scientific instrument, the James Webb Space Telescope, JWST. This telescope is here to delve into the depths of our universe. The JWST is no ordinary telescope. It's an engineering marvel and a testament to human ingenuity. While other space telescopes have done their jobs well, the JWST is unparalleled. It makes the Hubble Space Telescope seem like a mere speck in the vastness of the universe. The cost of this cosmic wonder? An astonishing $10 billion, a number so large it's hard to comprehend. This extraordinary project was the result of a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, with contributions from over 300 universities. But it's not just about the money, it's about the risks involved. The JWST is venturing into uncharted territory, pushing the boundaries of our knowledge, and taking us to places we've only dreamed of. After a successful launch, NASA recently announced that the telescope has enough fuel to last more than twice its baseline mission life. Since its launch, the JWST has achieved numerous incredible milestones. It traveled over 1 million miles to reach its orbit around the Sun, where it will remain permanently. During its journey, it successfully deployed its massive 5-layer sunshield and giant primary mirror, both of which had to be folded to fit into the launch vehicle. Now, after NASA has calibrated and aligned the telescope, it is nearly ready for full operation. One of the most fascinating moments came when NASA announced it had captured its first images of starlight. The first image taken by the telescope was of a star called HD 8446, resulting in a mosaic of 18 scattered bright spots from the star's light, captured by the 18 mirror segments on the primary mirror. Later, NASA released another stunning image of HD 8446, where 18 unfocused duplicates of the star were combined into a precise hexagonal arrangement. Once the observatory aligns the individual segments of the primary mirror, it will begin the process of stacking the images, merging them into one clear view. Thanks to its cutting-edge technology, the JWST will help researchers study the early stages of the universe, particularly the period following the Big Bang. It will assist scientists in understanding what happened after the first stars formed, a period known as the epoch of reionization. This refers to when neutral hydrogen was reionized, or made electrically charged again, by radiation from the first stars. This is only possible with a powerful telescope like the JWST. The telescope will also aid in the discovery of exoplanets, which are difficult to detect due to their interaction with their host stars. The JWST's powerful sensors will be able to observe these planets in greater detail, and, in some cases, even image their atmospheres. Understanding the atmospheres of these planets could help scientists predict whether some of them are tenable. As well as concentrating on planet arrangement, researchers are focusing on cosmic systems to comprehend how matter is coordinated on a huge scale. This will assist us in understanding how the universe evolved and how cosmic systems, like the winding and circular cosmic systems we see today, developed from various shapes over billions of years. One of the JWST's, James Webb Space Telescope, goals is to glance back at the earliest universes to better understand this development. Specialists are also trying to determine how we ended up with the variety of galaxies visible today and how galaxies continue to form and evolve. Most significantly, the JWST will help answer some of the biggest questions of all. Are we alone in the universe, and are we living inside a black hole? The JWST has already made some fascinating discoveries. For instance, it found compounds called polycyclic aromatic hydrocarbons, PAHs, around extremely massive black holes in 3 active galaxies. These carbon-based molecules, with their ring-like structures, are like the goth children of the universe. They are found everywhere, from distant galaxies to comets and even in our own solar system. PAHs are not just interesting because they could be the building blocks of life, but also because they help astronomers track star formation. When ultraviolet radiation hits these PAHs, they glow and emit infrared light, a transmission detectable by the JWST's mid-infrared instrument, MIRI. This usually indicates the presence of hot, young stars nearby. However, there's a twist. An inquisitive astrophysicist, Ismael Garcia Bernard from Oxford University, decided to investigate 3 active galaxies: NGC 6552, NGC 70319, and the famous Stephan's Quintet. These galaxies are millions of light-years away, cloaked in the darkness of space. What Garcia Bernard found will make your hair stand on end. In the central regions of these galaxies, where the black holes dominate, he discovered a large amount of PAHs. Sounds fascinating, right? Well, here's where it gets eerie. The radiation near those supermassive black holes distorted the PAHs, transforming them into larger, electrically neutral versions of themselves. The smaller, electrically charged PAHs disappeared into the void, consumed by the darkness. Now imagine being consumed by that darkness. But wait, there's a glimmer of hope. Or maybe not. The real question isn't whether we're alive but whether we truly exist. Does everything around us exist because of the black hole we might reside in? Could it be that everything is part of a black hole's event horizon? The boundary between the known universe and the unknown? Could we be living inside a black hole? The JWST is out there, searching for answers to these questions. Stay tuned because perhaps, just perhaps, it will make us rethink everything we thought we knew about existence. Reality might be far more twisted than we understand. In the fascinating universe of astronomy, few subjects have generated as much interest and wonder as black holes. These mysterious entities, once the stuff of science fiction, have captivated the imagination of scientists and the public alike. As researchers continue to explore the mysteries of the universe, black holes remain among the most puzzling phenomena in astronomy. The concept of a black hole was first introduced in the 18th century by the English natural philosopher John Michio, who speculated that objects with a gravitational pull so strong that even light could not escape them might exist. However, it wasn't until Albert Einstein's theory of general relativity in 1915 that black holes were mathematically predicted. These regions in space, where gravity is so intense that it distorts spacetime itself, have since been the focus of extensive study, and every discovery about them seems to lead to even more questions. One of the most fascinating aspects of black holes is their event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon marks the point where the gravitational pull becomes overwhelming, and this area is often described as a point of no return. Anything crossing the event horizon is inevitably drawn toward the singularity at the center of the black hole. The singularity, a point of infinite density, is where our current understanding of physics breaks down. The equations governing general relativity no longer work under the extreme conditions inside a black hole, and the mystery of what happens within the singularity remains unresolved. The study of black holes has revealed an intriguing paradox. While black holes can swallow matter and light, they also emit radiation, a phenomenon known as Hawking radiation, predicted by physicist Stephen Hawking in 1974. This radiation results from quantum effects near the event horizon. According to quantum theory, particles and antiparticles constantly pop in and out of existence in space. Near the event horizon, one of these particles might be captured by the black hole, while the other escapes, carrying away energy. Over time, this process causes the black hole to lose mass, potentially leading to its eventual disappearance. However, this radiation is incredibly faint, making it nearly impossible to detect with current technology, and its effects are negligible for black holes with masses much larger than the Sun. Interestingly, despite their name, black holes are not empty in the traditional sense. While they do not emit light, they interact with their surroundings in powerful ways. When matter falls into a black hole, it forms a hot, glowing accretion disk of gas and dust. As this material spirals toward the black hole, it heats up due to immense gravitational forces, emitting radiation across the electromagnetic spectrum, from X-rays to radio waves. This emission allows scientists to indirectly observe black holes, even though they cannot be directly imaged. In some cases, astronomers have used this radiation to map the environment around black holes and even measure their size and spin. Additionally, black holes can also produce powerful jets of energy, known as relativistic jets, which can extend for thousands of light-years. These jets are thought to be formed by magnetic fields generated by the spinning black hole and the surrounding accretion disk. As charged particles are accelerated along these magnetic field lines, they can be ejected at nearly the speed of light. These jets are often observed in active galactic nuclei (AGN), where supermassive black holes reside at the centers of galaxies. The energy and material expelled from these jets can significantly impact the galaxy, influencing star formation rates and the evolution of cosmic structures. Recent advancements in technology, especially with the launch of the JWST, are allowing scientists to probe the farthest reaches of space and investigate black holes in unprecedented detail. The JWST's infrared capabilities enable it to peer through cosmic dust clouds and observe objects too faint or distant for other telescopes to detect. This will help scientists understand how black holes grow and evolve over time. Observations of distant galaxies and the supermassive black holes at their centers will provide critical insights into the formation of these cosmic giants and their role in shaping the universe. Another exciting aspect of black hole research is the possibility that these enigmatic objects could hold the key to understanding the nature of quantum gravity, a theory that seeks to reconcile general relativity and quantum mechanics. At the heart of a black hole, the singularity represents a point where both quantum effects and gravitational forces are extreme. Studying black holes might offer clues about how to unify these two fundamental theories of physics, which currently operate under different sets of rules. Moreover, the study of black holes challenges our very understanding of reality. Near the event horizon, the fabric of spacetime is so distorted that time itself is stretched. This effect, known as time dilation, means that time flows more slowly for an observer near the black hole compared to someone farther away. If an astronaut were to fall into a black hole, they would experience time differently than someone watching from Earth. This strange aspect of black holes highlights the mind-bending possibilities of spacetime, pushing the boundaries of our understanding of the universe.